Video for Stat 420. Don't cheer too loudly, I can hear you through the computer. So we've been working on Metropolis-Hastings Algorithm in a different kind of case for our last example, the Bayesian setting. So in this setting, we have our goal to sample from the posterior distribution, which also happened to be a beta distribution. And our inputs, we want to be really clear here about our variables. N is the number of trials for the binomial distribution. X is the observed data. And we also need to have inputs for our prior distribution, so alpha and beta. Remember, if we set those to 1, that was our flat, uninformative prior. We also need how long to generate our chain, how many steps to run this, and the initial starting position. You might notice that earlier when we were deriving all this, we had M was the amount of data, how many times we repeated our binomial experiment. Here, we're going to be inputting that observed data, so no need to worry about it. We can grab the size from the data we input. All right, so we want to, from those values generated, we're going to output the theoretical and empirical means and variances. And it'd also be nice to check out the generated values from the chain. So here's our function. Again, be very careful of our inputs here. N is our sample size for binomial, number of trials, our observed data X, alpha and beta for our prior distribution, and then N and X are features of our chain, how long to run it, and our initial position. So the whole first part should look kind of familiar from the other examples we've done on our Metropolis-Hastings algorithm, just in the context of the Bayesian example here. So M's the length of our data, and then we've got our initialized as storage for the chain and started at that initial position. So we're going to go through the chain here, generate our proposed value from the uniform, calculate that ratio in rho. If you're looking at this, you might say it looks kind of strange. If you remember, we had P over, Y over our current position to the alpha star minus 1. This could potentially be a really tiny number. Oh, we also had kind of the same thing here, 1 minus Y over 1 minus P of T to the beta star minus 1. And, these guys could be really small terms. And, for example, beta star could end up being a really big number. So if I have a really tiny probability here, raised to a really high power, then I might not have enough room to store that in R with any amount of accuracy. So we've seen this trick at the beginning of the semester. One way we often might do this is take the log of whatever our function is. I'm just going to call this rho to represent that ratio. Might do the log of the ratio. So then now it becomes multiplication and addition. So I've got the alpha plus 1 here. So I've got the log of this value times some number, so it's easier to store. And then in the end, we exponentiate, so we're not changing the problem at all. So that's all this expression for rho is just taking rho, the log of rho, and then exponentiating to undo that, but just helps with the storage. Try it without it if you want and see if it can still handle storing those really tiny values. All right, and then our check for accepting or rejecting. We accept with probability rho, reject with probability 1 minus rho. So our update is either go to state Y or stay exactly where we are. And then our outputs here, let's calculate our theoretical mean and variance. So we know the mean and variance for the beta distribution. So we had this before. This is our sum of the x's over plus alpha, and then our alpha star plus beta star down in the denominator, and this expression for the variance. Those were on the previous page in our notes. Then we can calculate the empirical values for mean and variance. And notice here, said we're removing the burn-in period. You remember earlier graphs where our chain was hopping around for a while before it finally converged. So toss out the first 1,000 observations, throw those away, and then find the mean of the end of the chain where hopefully it started converging. So mean and variance of our chain after tossing out that first bit. And then we'll report all those results in a nice table. So to plug in some values here, do an example. Let's have a binomial experiment with n is 10, probability of success is 0.35. I don't know why the L disappeared here. So we're going to generate two different data sets. X1 is going to have a sample size of 1. X2 is going to have a sample size of 50. And we'll use n and p. So I've generated data with a known value of p of 0.35. Okay. And I'm going to see how that data informs my posterior distribution. Am I getting something around 0.35 is the most likely value, and really large probabilities are really small or less likely. So we're going to, again, run two chains, giving two different pieces of information, the small sample size, the big sample size. So for our prior, let's use alpha and beta of 2 and 5. And I'm guessing that those are going to give us a distribution that looks kind of like this, where smaller values are a little more likely. Come up with some random initialization between 0 and 1, and run the chain for 3,000 steps. So let's check out our results. Remember, we had two cases here. Trial 1 with 1 observation, trial 2 with 50 observations. And we can see in both cases that the empirical mean and variance match the theoretical mean and variance pretty closely. I'll just make that comment here. Theo and empirical close. Okay, so theoretically we know the distribution of the posterior, and the mean and variance of our chain after it's converged are also close to those theoretical values. I also want to point out, we mentioned the effect of increasing the sample size on the variance. Take a look here. The more data we have, our variance definitely decreased. So maybe make that observation. Variance did decrease as amount of data increased. Okay, so again, comparing this 0.012 to the 0.00046. And then also notice the role that our prior plays. So here's the mean and variance of our prior. So this is kind of mu of p, sigma of p. If you want to think about this theoretical, this is mu of p given the data. This is, well, I'm pointing to the variance. This guy is mu of p given theta. Here's mu of p given our data x. So those versus our posterior means versus the mean just based on our prior belief, just plugging in alpha and beta of our prior distribution. You'll notice when the data set is small, these guys are a little bit smaller, closer to the theoretical or the prior distribution. When we have a bigger data set, then our theoretical or the posterior distribution isn't as reliant upon the prior distribution. And finally, notice the data was generated using p of 0.35, and our results indicate that 0.35 is a fairly likely value since our means of the posterior distributions are near that. So just a couple of suggestions, and I might include this in a homework. It'd be interesting to vary the values of alpha and beta and see how that changes the impact on these two different sample sizes. And it also would be nice to output the values for the chain and construct a histogram so you get a sense for that actual distribution of the posterior. All right,